Okay, question 19. We have a spacecraft entering the atmosphere of Mars. It must decelerate to land undamaged on the surface. So here we have the spacecraft and it is traveling in this direction and is entering the atmosphere of Mars. The first question asks us to calculate the kinetic energy of the spacecraft given the mass and the speed. Now you have to watch out here. Speed is in kilometers per second. So that's 5,500 meters per second. And you put that into the formula of a half mv squared. So it's a half multiplied by 610 multiplied by 5,500 squared. And that should give you an answer of 9.2 times 10 to the power of 9 joules of energy. Okay. Now, the next question is showing the parachute opens and the spacecraft begins to decelerate. And it says, explain with reference to Newton's laws of motion why displacing the atmospheric gas causes a force on the system. And what it means by force on the system means the force on the parachute and the spacecraft, and why this force causes the system to decelerate. So there's many different marking points here to pick up 4 marks. So I've mentioned that the parachute accelerates the gas particles. Okay, so it applies a force on these gas particles to move in this direction. Okay, so and that's due to Newton's second law. Okay, so this is where you start off from. So the parachute is pushing on all of the gas particles and accelerating them by applying a force. You could talk about there's a rate of change of momentum of the gas particles, and that's directly linked to Newton's law, and we have to mention and reference Newton's law as much as possible. So the gas particles, once they've been pushed that way, we know that every time we push something, there is an equal and opposite push back in the opposite direction. So when these gas particles are pushed this way, there is an equal but opposite force back on the parachute, and that is Newton's third law. So mentioning that will pick you another couple of marks, and referencing that this is to do with Newton's third law. So that means now there is a force acting against the parachute, against the direction of travel. And we know this force is air resistance, also known as drag. We can refer to it often as the work done against the parachute. And what happens is the drag against the chute is greater than the weight. Okay, so we've got a weight that's driving it forward, but then we've got drag in the opposite direction, and the drag is greater than the weight, and therefore we have a resultant backwards force against the direction of motion, and as a result we have a deceleration. Okay, so if you look at your mark scheme, you'll see many points which I've discussed, and you have potentially got, if you look, there's a tick there, there's a tick there, there's a tick there, there's a tick there, many different points you could have mentioned, and then there are a couple of more ticks there. There's 6 possible points that you could have mentioned, and there's lots of options in the way you could have attempted this question. So it's ideal if you were to look at the mark scheme and see what other things you could have said. Now, the next question, I think this is one of the most challenging questions on the paper, and I think this is the best way to look at it. So, we've got, remember, this is just my picture of the chute coming down. Remember, the chute is moving downwards. So you got downwards weight, mg, and drag against it. Now, I'm going to say that the net force mg minus d. Now we know that the drag is greater, so the net force we're expecting that to be negative. Okay, and that's okay. That will yield a negative acceleration, which shows us that it's decelerating, which is okay again. So we know, and the reason why I've chosen that is because we're moving downwards. So I've said the downwards direction. Let's keep that as a positive. So that force is positive as weight, and the drag acts against it, which is negative. Okay, so that will yield a negative resultant force that signifies it's against the direction of motion, which is okay. And that equals mass times acceleration, which is the net force. Okay, so that's the net force, and that minus that will give you the net force, and we're expecting that to be negative. So we know that if this is a constant deceleration, a will be v squared minus u squared over 2s. And the reason why I've gone down this route is because they give energies in the question, and I don't want to mess around with masses and distances, and so I want to try to get this into the energy form. So what I've done is acceleration is v squared minus u squared over 2s. That's me using the one of the Suva equations and rearranging them in the form of A. And now if we look at this carefully, that looks very similar to kinetic energy. So what I'm going to do now is I'm going to move that S, which is distance, onto this side. So multiply out. I'll get mg times S, which is mgh, and drag times by distance. That's the work done against um, the gas particles. And then we've just got a half m, which is m over 2, and then v squared minus u squared. And we can see that's a half mv squared minus mu, half mu squared. So that's the change in velocity. So this is the GPE, and this is the work done against the atmosphere, i.e. the thermal energy loss worked in against friction, sometimes we say, a drag, and this is the change or loss in kinetic energy. So we have the mass, which is 610. We're trying to find g, which we leave. 49 is distance, that the vertical distance that the spacecraft has lost. And in that distance, we have got an energy, and that is transferred from the system to the atmosphere, is 3.3 times 10 to the 5 joules. So that there is energy, force times distance, which we've got an answer for. And then this is the um, loss in kinetic energy. Now, if we look at this closely, we know that the final speed is going to be smaller than the initial speed. So then v squared minus u squared should yield a negative answer. So that's why I've put minus 2.2 times 10 to the 5. And this is one of the things that most students would have made a mistake on. But nevertheless, you would have picked up at least 2 marks if you didn't. Now, if we move everything across, we end up with 1.1 times 10 to the 5. And that equals 610 g times 49. Rearrange that, and that equals 3.7 meters per second squared. I think this is the hardest question on the paper. If you got it, excellent. If not, any mark was a bonus. Now the next question is that we've got dust from the surface of Mars can enter the atmosphere. That increases the density of the atmosphere significantly. Deduce how an increase in dust content will affect the deceleration. That's a perfect diagram, and that's a perfect example of us helping us to answer this question. So if we have more dust in the atmosphere and more density, that means there are going to be more collisions per second with the atmosphere, and that's going to increase the drag. So that is going to get larger. That means that the net force against the motion is going to get larger. This will increase in net resistive force, which is mg minus drag, which we've talked about here. And if that gets bigger, more and more negative, that means that we're going to have bigger and bigger. This will increase, and hence you'll get a bigger and bigger deceleration. So again, your mark scheme will use a few different techniques of saying the same thing. So here you've got several options in the way to say the same thing, but cross-check and check if you've picked up some marks on that. And if you haven't, that's the idea behind this question.